Hello, and welcome to the Scientific Adventures of Beardman. Today we're on physicsclassroom.com under the topic Electric Circuits, and we're looking at a concept builder titled Electric Current. Okay, and so let's start by talking about what is electric current. Well, we can see that electric current, first of all, it's the symbol capital I. That won't tie into this concept builder, but it's important to know that moving forward. Capital I is what you'll see in formulas is the amount of charge that passes a point in a circuit in a given amount of time. It's usually measured in coulombs per second, which is an ampere, or capital A. It also goes by lowercase a. Okay, one of those where the capital and lowercase are often disagreed depending on the physics textbook. I know, strange, huh? So, in other words, when we hook up a battery, that's going to produce a voltage, which we'll get to a little bit more later, but it means that the electrons over here have more energy than the electrons over here. And so those electrons will get pushed through the circuit. Now, one thing about the current, you'll see the current here going in this direction. Why isn't that doing my little marker thing? There we go. Going in that direction. When we said electrons would be going this way, well, that's because conventional current, with the first people who tested this, used conventional current as flowing in the direction that a positive charge would flow. At that time, they didn't even know that there were electrons and protons. And so they just said, hey, we'll call this side positive, and we'll say that it's the direction a positive charge would flow in this wire. Okay, so that's going to be our conventional current. Everything is tied to that in electronics, so it'd be, I think, too complicated to change to the direction the electrons actually flow. So anyways, it's the direction a positive charge would flow. As we've already learned, protons don't move out of their nucleus to flow through a wire. It's the electrons that are moving. And so this is just the concept. The conventional current goes this direction. So as the battery with its voltage, its higher energy and lower energy, pushes the electrons around, that makes the current flow through the wire, through the light bulbs, and so on. Now, when this gets hooked up, every single electron that's in this wire or in these resistors, they're called, they could be a light bulb, okay? Every electron begins to move at once, okay? They all feel that energy from over here, and so the electrons get pushed this way, which means we have a conventional current going this direction. Okay, that's getting a bit clogged up there. Let's get rid of some of those electrons. So then one thing about that current is it's the same everywhere in a series circuit. Okay, so whatever the current is here, let's just say it's 2 amps. Then over here, it has to be 2 amps. And over here, it has to be 2 amps. And over here, it has to be 2 amps. And through the battery, it's 2 amps. Okay, because we can't get like a buildup of charge. So if the electrons are flowing through here and there was more current here than here, well, then we're going to get a whole lot of electrons in here, just building up and building up. And well, electrons repel each other. So that just never happens. If we're in a series circuit, the current will be the same everywhere in the circuit. There are lots of questions throughout the concept builder where it has a different current in different places, and you say, that's wrong. The current has to be the same everywhere in what's called a series circuit. A series circuit means there's only one path around here. We'll get more to that later. Everything you'll see in this concept builder is a series circuit. Okay, now a couple more things that you'll need to know to go through this concept builder. The first is that when there's more resistance, that makes it harder to flow. Well, what is resistance? Well, wires to some degree, but not very much. But things like light bulbs or toasters or whatever it is, your computer, those things provide resistance, meaning the electrons don't flow through it super easy. They can flow through it, but there's a certain amount of resistance that we'll be putting numbers to later on. For right now, what you need to know is if we looked at a circuit that did not have these light bulbs, just this light bulb, and then we added more light bulbs, well, now these electrons have to not only push their way through this one and this one, or we could say the current has to push through this one and this one and that one. It has to go through 3 things instead of just one. That makes it harder. So the more light bulbs in series creates more resistance. More resistance makes it harder for current to flow. Okay. The second thing is you'll see them adding batteries. So instead of just having one battery over here, they might have 2 or 3 batteries. If those batteries are hooked up in series, since the batteries create voltage, more batteries in series create more voltage. So if we have 1, 2, 3 batteries, that will have more voltage than one battery in series. More voltage makes a bigger electrical current. So if we're pushing harder, that's going to make the current bigger. Instead of 2, it'll be 3. All right. A couple of conventions that they use in physics classroom that is not super common anywhere else. And that is these 3 things. You can find this under the Help Me section if you'd like. So first of all, the arrow tails. So you see the arrows that represent the current. Okay, the number of these little tails that they have on here indicates how strong the current is. In other words, if we added that's supposed to be a triangle. Yeah, there we go. If we added something with just like 2 tails, that would be a weak current or a very little current. And if we had like, I think they say 9 tails, then that would be a strong current. And here we have like 4 tails, so that would be a medium current. Okay, so arrow tails tells you the strength. So if you saw just a couple of arrows, or let's do a lot of tails here, and then over here you saw just like 2 tails, you'd go, something's wrong with this. This can't happen because we can't have a different current here and here. It has to be the same current throughout a series circuit. By the way, notice how they hook up the batteries here. This is a series circuit because there's only one path through there. They can't go here. There's no wire there. They have to go through like that. So series circuit, there's only one path. Okay. So arrow direction, that's pretty obvious. Whatever direction the arrow is pointing indicates the direction the current's going. The current will always go from positive, because remember, it's the direction a positive charge would flow, and a positive charge would be repelled from a positive, so it'll go away from it. And then it'll continue that way around the circuit. This one, the arrows are going the same direction around the circuit, and so everything looks good. They're going the same direction, and they're flowing away from the positive. They're being attracted to the negative. That is conventional current. The final thing you'll see, talk about light bulbs. This is how they draw a light bulb over here. And they have these little, they call them starbursts coming out. The more lines they have coming out, the brighter it is. Okay, so if it looks like this, not very bright. If it looks like this, that means it's very bright. Okay, and so when you get a lower current, you'll tend to get dimmer light bulbs. When you get a very high current, you'll get brighter light bulbs. All right, so let's take a look at a problem here. So, like I said, it looks like this. And so you have 3 different types of problems. Well, the first one, the first activity doesn't have the arrows like this, and it actually doesn't have the starbursts. It just mostly is asking you questions that are answered on this page. Is it going in the direction a positive would flow? Is the current the same everywhere in the circuit? Okay, so just read the questions carefully and apply those answers to it. Then the second concept, the second activity, has you look at changes to the circuit and imagine what's going to happen to the current. Okay, and so that's where you're going to be applying these two situations. Is there more resistance or more voltage, and what's that going to do to the current? Okay, so you might see them talk about switching the type of bulb here. If it gets more resistance, that means you're going to have fewer tails on your current. If it gets less resistance, meaning things can flow easier, then you'll see even more tails drawn on your arrows. Remember, it always has to be the same number of arrows up here and here, and your multiple choice choosing between several options. It could also add in an additional bulb. If you add an additional bulb, remember when you get more bulbs, that's more resistance, and therefore you will get less current. Okay. Finally, you could have different numbers of batteries. Okay, so you'll see it either goes, I think it always either goes from 2 batteries to 3 or from 3 to 2. Okay, so you'll just see one of these missing here and there'll only be 2 batteries in the system or something like that. Remember, more batteries provides a bigger push because they're connected in series. They gain energy, gain energy, gain energy. They have 3 times as much energy as one battery, and that's going to push them harder around or push them faster around the circuit. Okay, so that means you'd see more batteries, means you'd get more lines over here. The final activity has you decide which things cannot work, which ones violate laws. Okay, by laws, they mean those things that I told you on that second page. In other words, look for the current going the wrong direction, not heading away from the positive and towards the negative. Okay, look for the current being different in different places, 2 lines down there and like 9 lines up here or whatever. Okay, that would indicate that it can't work. It has to have the same current everywhere. Otherwise, it would violate laws of electrostatics. It would bunch electrons up. They don't do that. They keep spread apart. So in a series circuit, the current has to be the same everywhere. You might see 2 light bulbs in series with different amounts of starbursts. That's not possible. If they're the same light bulbs, and I believe it'll say they're identical, then they'll have the same current through them. They'll produce the same voltage. They'll have the same brightness. Okay, so make sure those are the same. And when all else fails, come back and take a look at this page. It gives you all the tips that you need to know in order to catch anything that's incorrect. Oh, by the way, the very first one I forgot has this definition in it, or a similar definition. All right, well, good luck puzzling out the electric currents, and I hope they don't sweep you away. Oh, I almost forgot. I have this little tool booth guy because of the definition of current here is the amount of charge that passes a point. So I like to imagine a little toll booth guy there, and every time an electron goes by him, he counts it. And so in 1 second, how many electrons does he count? Well, of course, we don't usually count electrons because there's so many billions and billions of them. Instead, we do it in terms of coulombs. You get a certain number of coulombs going by each second. If it's 2 amps, that means 2 coulombs worth of charge have passed the little toll booth operator, checking out how much current is traveling through this circuit. Thank you for joining us today on the Scientific Adventures of Beardman. Enjoy the concept builder, learn a lot about electric current, and we'll see you next time.